Okay, very big welcome to tonight's meeting at Pennine Ham. And we're really pleased to welcome Bernard ON4CGX, who's our speaker tonight on radio astronomy. A bit more about that in a second. But we're very pleased to welcome a number of visitors from Belgium and Holland to our meeting this evening. We're delighted to have you come and join us and hope you find that some of our meetings in the future might be of interest. Feel free to join the mailing list for our meetings and you'll get an invite. If it looks interesting, by all means come along. Just out of information, our next meeting in a couple of weeks' time is Anthony Luska, K8ZT, who's going to give us a talk about busting myths of contesting, which is a talk he gave to one of the big ARRL events in the US, and he does online as well. So he's going to give a talk about that, which is it was a very enjoyable talk he gave, and we said we would get him back to give us a talk on contesting at some stage. So that's my news. So Bernard ON4 Jeff ON4 GT ON8NT was at Leuven, where you and others gave talks on all kinds of subjects. Radio astronomy was one of them, APRS and lots of others as well, that are related to radio, but not strictly amateur radio, of course. But I just wanted to start by saying that the study of space, and particularly radio study of space, which is what radio astronomy is, isn't it? Listening for signals around the universe and the solar system that can be picked up here, is a subject which is pretty fundamental to amateur radio, because one of the earliest discoveries that all of us in this room here are radio amateurs know, and it wasn't that long ago, it was in the early 90s, I can't remember the exact date, in the early 1900s, was the discovery of the ionosphere. And the scientists who discovered it came to the conclusion that because radio signals bounced off this layer that they call the ionosphere, it would be impossible for us to hear signals from outer space. And that was the conclusion they came to, until fairly quickly, I think, that was overturned, and science moved on, and people discovered that we could indeed hear radio signals from elsewhere in the not just our own solar system, but from others as well. So, Bernard, I'm going to hand the microphone over to you and let you take us on the journey. And Bernard, by the way, and I'm not going to embarrass him here, but he did say to me when we spoke a couple of weeks ago, he said, I want to apologize in advance, Nick. My English is not that good. And actually, his English is superb. And it's certainly a million times better than any attempts I've got to speak Flemish or Dutch or indeed German. I can just about get by in all these countries as a tourist, attempting to speak some language. But Bernard, not as good as your English. So I'm going to hand the microphone over to you.
Thank you, Nick. The reason, because there are people from my local radio club here, is they want to laugh at me with my English, Nick. So that's the only reason. It's not the issue that was interesting. Can I share my?
Yep.
Yeah. Do you see my screen?
Not yet.
Not yet.
Yep, just come up.
Okay.
Just started to screen share. There we go. Radio astronomy experiments. ON4CGX. Yep.
I want to speak about some issues in radio astronomy experiments that I have done the last years, and who is very interesting to do by yourself, and where you don't need so much energy and so much material for it. What I want to talk about this evening is first some units we are using when we are talking in space. Something about meteor scatter, aircraft scatter, and interferometry. The hydrogen line, which is very interesting and is the major part of this presentation. Something about pulsars, and then at the end, something about DSN, the Deep Space Network, the network NASA is using to communicate with the spacecrafts in our solar system. So the units, I am not familiar with feet and foot and miles and so on. I'm more familiar with the meters and kilometers. I'm very sorry for that. So you have to do it this evening with continental units. When we're talking in our solar system, we have a unit who is commonly used as the astronomical unit. That's about 115 million kilometers. That it's used because that's the average distance between the Earth and the Sun. So they're using it for comparison and distance with the distance between Earth and Sun. So it's a light year. It's also a unit who is used. That's the distance light is traveling in a year. That's not a normalized unit. And you have an old unit, the parsec, but in our Milky Way, it's very commonly used, the parsec. That is 3.26 light years. Very strange unit, but that's, if you look at it, it's the distance when you have an angle between from the object to the Sun, when you have an angle of 1 barsecond from the Earth, that's 1 parsec. They have used it to measure distance of objects in our Milky Way, because you can measure the angle in the summertime, and in the wintertime the Earth is on the opposite side of the Sun, and you have the double of the angle, so you can calculate very easily the distance between the object and the Earth. That's why they have made the parsec. In the Milky Way, they always calculate with the kiloparsecs, the thousands of parsecs. Meteor scatter, that's when you look at the observation stations for astronomy, if they have lines with radio, it's always with meteor scatter. For example, we have here in Belgium, we have 2 observation stations in Zellebeke and in Durbe. Zellebeke is just at the south of Wipers in Flanders Field, and Durbe is in the French talking part of Belgium. They have a beacon on 50 megahertz where you can receive very easily. You have also a beacon on 2 meter, 144 megahertz in Graaf in France. And you can use any beacon you like in England or in Belgium or in any place to observe meteor scatters. What is a meteor? That's a piece of rock who is entering the atmosphere of the Earth. And because of friction, it's exploding. And this explosion gives an electromagnetic distortion who is measurable with our receivers. How we do this? You have, for example, in Zellebeke and Durbe, they have an antenna, a cross dipole on 50 megahertz who is aimed vertical. If you have a receiver and you take with your receiver the audio on a spectrum with some software like Spectra or Spectrum Lab, or you need an SDR dongle. An SDR dongle, you have directly the spectrum. You can see here the carrier, and you can see also the vertical pings who are passing. That are meteors who are passing, because the velocity is very great, so the Doppler is very great, and you see the meteor passing the carrier. So the more you see of this phenomenon, the more meteors are entering the atmosphere. These lines you see here, that's an airplane who is passing. You see here he's on a very long distance, a very far distance. He is coming near and nearer the beacon. The moment he is above the beacon, the velocity between the beacon and the airplane is 0, so the Doppler is 0, and then he is going away from the beacon, so the Doppler is rising. That's a very interesting thing. I use the beacon here of in 70 centimeters from Brussels. you can see the planes on the airport landing and starting in Brussels airport on your receiver. Graph is very interesting. What is Graph? Graph is a beacon who is a military beacon who is put in France near the Swiss border. And it is constructed, as they say, to control the graveyard band. What's the graveyard band? That is the band of around the Earth, about 100, 200 kilometers above the ground. That's the place where all the garbage of launching all the spacecrafts is rotating the Earth. It's also the band where the old satellites are decommissioned and going in that band and probably also go through the atmosphere and burn up in the atmosphere. So to control all this garbage, they have built this radar, but I think that radar has also other meanings because it is a military beacon. You see here the flat antennas, and 100 kilometers above of it, they are the receivers. That's 2 or 3 football fields long ground planes with vertical antennas. Every pole has 4 antennas, 4 dipoles. I think it's a Doppler paler. It's something who is calculating direction, I think. If you look at this beacon with a 9-element Yagi antenna from Tonna, which I have, that's a Yagi antenna of 2 lambda boom, you can see reflections from the moon from that beacon. It's very strong. So also in England. That's a screenshot taken with SpectraView. You can also use other programs to see it, or an RTL dongle. You see here the carrier, these stripes that are aircraft scatters, the horizontal stripes, that is again the meteor scatter, and here on your right side you see the reflections from the moon, and that's very strong. If you have, you just have to put your antenna in the direction of the moon the moment that the moon is about, for us at the south side, you can see the moon bouncing. And the frequency is 143.050 Hertz. So we can do that with our own equipment. You don't need something very special. That's a transmitter, one of the transmitters. That's a container, and that's a flat antenna. I don't think they use 100 watts. I think they use a little bit more. You can find it also, Papa Echo 1, Italy Tango Romeo has got a website of it with some explanations. If you Google on radar graph, you find documentation about this radar. That's the receiver, which is not my receiver, unfortunately. You can use also a beacon. You have also beacons in England. You can use, just aim your antenna to a beacon. Your low frequency, the audio you get on a spectrum, and you see the reflections of all the things who are passing. Meteor scatter, it's a very interesting thing. You can use Spectrum Lab for the guys who use VSGTX. You can also use this spectrum. Any freeware program is available for this meaning. Aircraft scatter is just the same, but we are using an aircraft and not meteors. They have programs for it. For example, Delta Lima 2, Alpha Lima Fox have made a program, RCF, aircraft scatter. The meaning is you make a connection with another ham radio by scattering on an airplane. For that reason, you need to make a sketch with another person, and you need to know when a plane is favorable in your direction to scatter on it. So that program helps you. For example, I have here my location. I have put it here, And this location is a beacon I have found in England, the GB3 megahertz Mike Hotel Zulu. I think it's known by you. You see here, there are two planes who are on the screen. The one is red, and the other is some kind of orange or some kind of purple. That plane is favorable to do some scatter. That plane not, but it will be favorable. If you see at the bottom here, they have put the Earth flat, and they've put here a dot where that plane is, so you can calculate where you have your scattering point. I know in Holland, Papa Echo Zero Sat will know it. They have published a paper that they have scattered on the Mir station when it was decommissioned, and it works also. But you need some power. That's the disadvantage. You need some power to receive the other end. You can also use ISS to do it, but I don't think they will be very happy with it. Interferometry is also something that's very interesting, which I have done. The principle is you have two antennas from a distance from each other, and the source is so far away that the wave who is coming in is a parallel wave on the two antennas. You have a phase shift on the two antennas, and you can measure that. That gives them some few advantages who are very interesting. For that, I have compared two antenna systems. My first antenna system, that was my EME antenna setup. It doesn't exist anymore. It has passed away by a storm. 4 times 12 elements on 70 SEMS. What have I done? I have aimed it on 45 degrees to the south, and I have recorded the noise level 24 hours, and I have made a recording of 24 hours of the noise level I have received with that antenna. Fortunately, the Earth is moving, so when you look at the sky, you see all the sky passing your antenna, and that's a very interesting thing. I will show you something. There is a program who is called Radio Eyes. It's a freeware program, and I will open it here. So, do you see that program? I hope. What gives it? It gives in real time. You take the Earth away, just the Earth is one point, and you look to our universe or our solar system. What you see here, this dotted line is the horizon. So everything below this horizon you can't see. What you see here, this tail, this colored tail, that's the Milky Way. That's the Milky Way who is passing to our heaven here. This circle is the beaming of my antenna. So you see, for the moment, we are in a very cold place on the sky. If I go further in time, for example, I will try 24, voila. I take another day, 10 hours. You see that because the Earth is moving, that the Milky Way is passing our antennas. So we are expecting when the Milky Way is passing our antennas, that our level is increasing. So that is very beautiful in theory. In practical, we have so much local distortion that you cannot always be sure that an increase of noise is an increase because of the solar, because of the Milky Way, or it is a local distortion. That's almost impossible to do. And with interferometry, we can do it. What I have done is I have taken two antennas on 70 SEMS. I have not built it especially. I have those antennas, so I have used them. So it's a 2-time doppel 8 antenna. It's a very good design from the Roothamel antenna book from our German friends. I have modeled this antenna. It has one main lobe and two side lobes. And I have put, I hope you can see it good on this antenna. I have put two system antennas beside, some 20-25 meters from each other away. I have modeled these two antennas, and you see that this lobe is shattered. What is the result of it? If the sun is passing, that's here a recording when the sun is passing my antenna. You see here one side lobe, the main lobe, and you see the other lobe. Why it isn't a local distortion? Because you have a sinusoidal function in it. Because of you have the two antennas who are some moments in phase, some other moments in counterphase, you have those up and those down. So you are sure this is the sun we are measuring and not local noise. That's just a zoom from the sun who is passing. That is an image of 24 hours. So I have made a recording of my audio for 24 hours, and I see, for example, here three different observations. The one is a quiet spot in space. The two is the tail of the Milky Way, and three is the sun. If you look at the two, that was that moment that here my antenna was aiming to the tail of the Milky Way. The one was here, that was a very quiet place in the sky. And here was the sun. Three was the sun who was passing through the antenna. It is, you see on the antenna I'm using, it's a very great antenna because a very big antenna on 70 cents. You don't need to build such an antenna. You can do it on 10 gigahertz. If you have two dishes with two LMBs, there's a low noise blocks you are using for Q100. You put it a few meters apart, you can do just the same. Just summarize the two signals and put it on a receiver. And you can do magnificent things with it. With very low material. Just an RTL dongle as receiver is also good. That's the Milky Way as we know it. We are here somewhere, and that's the tail who is passing the sky when we are measuring with our antennas. The bigger your antenna, the more sharp you get pictures. If you do it every night for a few years, you can build a whole picture of the tail of the Milky Way, which I didn't done it. I don't have the time for it. It is also very interesting to do some measurements, which we otherwise not can do as a radio amateur. I know my antenna Doppelact has a theoretical gain of 12 dBd, and my EME antenna is 20 dBd. So, first, another thing you can do, I have here a zoom of 1 hour. You see, in 1 hour, we have 8 periods of my signal who is passing my antenna. If you calculate it, you can measure the distance between my two antennas and that's, I will not do the calculation here, but theoretically, the distance between my two antennas is 21.39 meters, which was exact the distance between my antennas. Just by measuring the period of the phase of my antenna of the incoming signal of these two antennas, that was 21 meters. You see here two shell flex coaxes, which I have found second-hand from a surplus, from mounting from GSM masts, and a combiner with a preamp. Nothing more. what you also can do with these antennas, that's measuring the gain of your antenna. So you see the difference between the plus and the min is about 500 to compare it to 2597. If you calculate it in dBs, I have a difference of my EME antenna and this antenna of 8 dB, which is correct because the one is 20 dB and the other is 12 dB. So I cannot do correct measurements of the gain of my antenna, but I can compare antennas to each other and tell exactly this antenna is 10, 15 dBs or 5 dBs better than the other antenna, just with an interferometer. Very cheap. If you want to buy equipment to measure antennas, it will be more expensive. So hydrogen line, that is the most interesting in radio astronomy, measuring hydrogen lines. What's hydrogen? Hydrogen is the lightest element who is existing, and it was with the Big Bang. It were only after the Big Bang we have only three elements in space. That was hydrogen, helium, and lithium. Hydrogen is the building block where the sun is built off, where the earth is built off, and we are also built from this hydrogen. It is still present in the space as a rest product of formation of solar systems, and we can measure it. What is a hydrogen? Very elementary. It's built of one proton and one electron. It's one electron who is on an energy level around the proton. As we know from the chemistry, if you put energy on that system, that electron is going orbiting on a higher energy level around that proton. And after a time, it is coming back to his normal rest position. And when it comes back to his normal rest position, it gives an electromagnetic wave. So you have several energy levels, but the first energy level is the most interesting because it's not a higher level, it's the electron who is, you can make a comparison as it has a spin flip. It is turning around itself and it's turning its electromagnetic fields from upside down. And that gives, the moment that it's going back to its normal situation, it gives an electromagnetic signal of 1420 megahertz, exactly. And that's something we can measure. This frequency is very, very accurate. They call this first energy level a spin flip. When you have a spin flip, it's very rare because you need two hydrogen atoms who are in collision with each other. If you have a collision that it's about every time, once in 60 years, you have a collision. And after that collision, you have a spin flip. And after 11 million years, that spin flip is turning back and it gives that electromagnetic pulse. So you have more chance to win the lottery as you have chance to see a hydrogen electron on 1420 megahertz. But because there is so much hydrogen in the universe, it happens all the time. That's the advantage of it. The most hydrogen line we are measuring coming from the Milky Way. In the Milky Way, we have a density of 100 atoms in a liter, in 100 atoms of hydrogen in 1 liter. For comparison, on Earth, 1 liter of air is 30 trillion molecules. So you see the density in the space is very low. Also, the chance for collision is also very low. How do we measure it? We have an antenna. We need a preamp. That's very necessary to have a preamp. and only an RTL dongle, not more. You can also use another receiver, but an RTL dongle is also very suitable for it. And we have a program, SDL Sharp. I think everyone who is using RTL dongles knows the program RTL Sharp. It has a plugin EF average for averaging your signal. So you have just need the RTL, the known RTL dongle. The preamp you can use, I have used an SSB Electronics wideband preamp who wasn't suitable because this preamp is amplifying everything very wideband, and that's not good. You just only have to amplify the bands of the 1420 megahertz. There is one LNA on the market who is very suitable for it from Noelec. They have also other LNAs who are very suitable. This is $38. It is constructed with 2 LNAs and a bandpass filter in it. It works very good, and it has an amplification of 60 dBs, 60 decibel. Thus you need a very big amplification for hydrogen line measurements. But it's worth it. The antenna, you can build one yourself. You can also find secondhand some antennas. This is a TP-Link antenna. This antenna is used for point-to-point communication on 2.4 gigahertz. Now, if you look on the internet for hydrogen line receiving, you will find people who are claiming that this antenna is also suitable for 1.4 gigahertz. And I have tried it, and it is effective. So it's working very good on 1.4 gigahertz. So you find it on internet. I think the price is about €100. So I think an 80-90 pound you can purchase such an antenna. The only thing you have to do is the reflector. You have to turn the reflector on the other side to have a good result. You can also use it for an uplink for QO100. If you have a station for QO100, you can use your uplink antenna and equipment for downlink for the hydrogen line. You just have to pass your antenna to another feeder. So here I think if you see on my picture, this is one I have built myself. It's just a plate with some copper wire with a holder for your feeder for the dish antenna, and you have an antenna for this frequency. Very simple to mate. That was a dish antenna of 2.4 meters I have used a few years ago. Very strange, but the result is just the same as you have with this antenna. So you don't have a better result with a better antenna. You can use already this antenna. That's the feeder of that antenna. The feeder I have made from a chimney, a piece of chimney with an N-connector chassis piece, and within it a piece of copper wire who is a quarter wave on 1450 megahertz. If you aim this feeder, only this feeder to the sky, you can also receive the hydrogen line. You don't need a great antenna. But I would not recommend you to use for the first time this feeder. Try with a better antenna first, and if you have some experience, you can use this antenna because the signal is very, very weak with that feeder. Also, the QO100. Most people have problems to aim a dish antenna to the QO100. Not a lot of people know that if you just take your LNB, your low noise block, and you aim it approximately to where QO100 is, if you have a good receiver, you can already receive the QO100. That's a very strong transmitter in that satellite. So you can do it only with the feeder. You don't need this antenna. What are the results of it? I have here some videos. What I have done is, I will just a minute, stop it. But what I have done, I have taken my program who is observing the universe, and I've put it on the lower side of my screen. On the upper side of my screen, I have put in SDI sharp. That's the EF average. I have put it on the upper side of my screen. And I have let run a program on my PC who is taking every 10 minutes a screenshot of my screen. And I have a bunch of pictures of screenshots, and I have put it together in one movie. And that's the movie that I have made with this constellation. So you see, you have this bubble here is the hydrogen line, and the moment we are passing the tail of the Milky Way, you see also reaction on the measurement of our hydrogen line. So that was with that TP-Link antenna. You can also calculate the Doppler shift, so you can calculate the velocity of the Milky Way who is passing your nose here outside. You can do a lot of nice experiments with it. It is a very nice thing to do with young people if you want to make people interested in radio astronomy. Also people who are just doing astronomy with telescopes. It's also interesting for those people to learn that there is also other things as not only the visible part of it. That was with TP-Link, that was another one. Voilà. The way you have to do it, the way you can do it, it's very simple. It's explained on the internet, on several sites, how you have to put your settings for STR dongle to have this result. It is more simple as it looks, and it's very funny to do. Pulsars, that's something very difficult to do. What's a pulsar? I have here a whole explanation, but the key is a pulsar, that's a sun at the end of its lifetime who is imploding to a black hole, and when imploding, it is putting all his mass together in a volume of something with a diameter of 10 kilometers, and it is rotating on a speed of 1 time per second or even faster. And this rotating gives an electromagnetic wave, and we can't measure that. But it is very, very difficult to measure. It is called a neutron star. It has a diameter of 10 kilometers and a mass of more than 2.16 times the sun's mass. What is happening? This black hole or this pulsar is rotating around his own axis very fast, between 2 milliseconds and 10 seconds, but the time it is rotating is very stable. It's more stable than a rubidium atom clock. So you can put your watch correct with that pulsar. The strongest pulsar we have is the B0329 plus 54. I don't know how they became, of how they giving a name to it. It is all about 3000 light years from us, and it is emitting 1500 milliamps on 400 megahertz with a period of 0.6 seconds. And you don't have to hurry, it will be active for the next 5 million years. So you have the time to put something together. What is a milliamp? A milliamsky, that is 0.25 times 0 and then 1 watt per hertz and per square meter. So a very low radiation is it, a very low power density is it, but it's one of the most powerful emitting transmitters we have in our universe. They say that you can measure it with a RTL dongle with a bandwidth of 2 megahertz. If you use an isotropic antenna, your power density of the signal who is receiving the Earth is 0.20 times 0 and then 3 watts per square meter. If you calculate it, that's a voltage level of 3 nanovolts on your antenna. For comparison, an EME signal, an average EME signal is 18 nanovolts on your antenna. So EME signals, Earth, Moon, Earth, is 16 dB stronger as that pulsar. So we need to search for a pulsar who is 16 decibel below noise level, who is very, very deep. Who can receive it? I am very jealous on our Netherlands college, on our Hollands college. If you ever pass the north of Holland, please visit Dwengelo. In Dwengelo, they have a dish of 25 meter who is used in the Cold War, who is decommissioned, and the radio amateurs are using this antenna. They can hear a pulsar and they can hear it also on LF. You can hear with your own ears that pulsar. If you look at internet to cameras, that's the website of the Dwengelo. I will try to find it for you. Those people doing amazing things, which I am very jealous on. Cameras Dwengelo.
The link is in the chat, Bernard.
Pardon?
The link is in the chat.
The link is in the chat. Okay, thank you. That's a telescope they have used. The first Venus bounce with the Dwengelo telescope. You see in the headers, they do amazing things. The first connection with the geostationary satellite they have also done. They have received signals from the Voyager 1. They are doing on daily basis or weekly basis, they are receiving pulsars, which I became, when I see that, I spit on the ground. I'm so jealous on these guys. I have tried for 2 years to find a pulsar and I didn't find it. What do you need? They say you need an SDR dongle. You need programs. You cannot hear it, so you have to aim your antenna to the pulsar. You must record your IQ signals from your RTL dongle for 2-3 hours. It gives a bunch of data, more than 30 gigabytes, and you have to process this data. There are programs who are written by radio amateurs, like Era Pulsar, to edit this software. So you have to record 2-3 hours, then you have to let your computer calculate a few hours Fourier transformation to look if you have found the pulsar, and at the end they say, no, you have found nothing. That's very frustrating. There were also other problems with pulsars. Here you see the axis on the base is the time, and vertical you have the level of your noise you're measuring. You see blue pixels and you see red pixels. Those red pixels, those are the pulsars. Every time, every 0.6 second you see the pulsar noise. The challenge is to isolate these red dots from the blue dots. That's the software who is doing it. They call this technique folding. What they are doing, they are folding your data in equal parts, and each part is the length of the period of your pulsar. They add all together, they make an average, so the pulsar's peaks must appear then. But I have never found a pulsar. Those are claimed results with pulsars, the Vela pulsar. I have found a website in Italy, Italy Whiskey 5, Bravo Hotel Yankee. He has built an antenna with a preamplifier and an USB dongle, and he's claiming every day I can receive the pulsars. I have built this antenna. Just a minute. Yeah, that's the antenna. That's the shield. I have thought if it doesn't work, I can keep chickens with it, so it's not lost. So I have put this in the yard. That was the day that my wife was finding out that she was married with an idiot who is calling this installation an antenna. I have also had the idea to build two of it, to do interferometry with it, but my wife didn't want to be married with an idiot who want to build two antennas of this kind. So that was an experiment who is not continued. So you have the antenna here, the preamp and the receiving. I have made in 4NEC 2, I have made a simulation of this antenna. It works, it really works, this antenna, but I have no result. The website from this Italian person doesn't exist anymore. So I think you don't always have to believe what they publish on it on I almost say on Italian on the internet, but I had confidence in that person because it's a person who has done Earth, Moon, Earth on 70 centimeters. There are other Italian stations, also Spanish stations who are doing EME, who have great dish antennas, 5-6 meters, who are also able to receiving pulsars. But then I have taken contact with the guys of Dwengelo, and they have told me on a very kind way that it's a very big challenge to receive a pulsar with that kind of material. That's what the Dwengelo, the PE9COM Dwengelo dish is receiving with the 25 megahertz dish, which is a very better result. If you have, I think, I don't know if they are doing, but Dwengelo has done every year. You have the YOTA, the Jamboree on the Air from the International Scouts Organization. And Dwengelo is then, that moment, is aiming their antenna of their dish to the moon to give young people the opportunity with a very small antenna with 50 watts or something to transmit to the moon and then hear their own echo signals with Web SDR from the Dwengelo telescope. So it's worth it to look when they are doing it or when they are programming it. It's a very interesting way of experimenting with EMA, because you can do it not only in CV or digital, you can always do it in SSB. So you can hear your own voice back via the Dwengelo telescope. You can hear it. I'm very jealous. So DSN, what's that? That's Deep Space Network. The NASA, also ESA, needs to communicate with spacecrafts they have sent to the other two in our solar system, like Mars, Venus, Saturnus, and so on and so on. And they do it with a network they call DSN. You can find it on the internet if you are Googling on DSN now. If you look at DSN now, voila. What you see, they have 3 places where they have antennas. In Madrid, Spain, Goldstone, America, and Canberra, Australia. Why these three places? Because if you look at the Earth from the North Pole to these 3 places, they are separated in an angle of each 120 degrees. So that means that wherever the spacecraft is in space, you can always have one station who can communicate with it. You can see here, for example, Madrid have a great dish and some smaller dish. This is communicating with Maven, this with Soho. The dish 53 is communicating with Europa Clipper. The 54 is communicating with all the spacecrafts who is around Mars for the moment. Goldstone is, for example, communicating with ACE. Canberra, it's night at the moment, so they are communicating with the JWST, that's the James Webb Telescope, and also LRO, that are the moon sondes who are orbiting the moon. So every station has its work to do. They have very good equipment for it, but we as radio amateur, we can also receive those spacecrafts, and you don't need so much material. I have a dish of 1 meter and it works for me. How do we do it? You see here, DSN have mainly 2 segments. You have the S-band and the X-band. S-band is on 13 centimeters, 202.2 megahertz. Mostly the S-band is used for all the probes who are less than 1 astronomic unit. So all the sondes who are between Earth and the Moon, using the S-band. X-band is 8.4 gigahertz, and that is used for the rest of the solar system. So even the Voyagers are communicating with 8.4 gigahertz. You also have communication 3345 gigahertz, and they are experimenting with laser light to communicate. But laser light has the problem, you have a lot of dispersion, and that's a problem they have to counter. So for the moment, we can also listen to the X-band. The challenge for S-band, it's relatively easy. If you have equipment on 13 centimeters, you can use it for the S-band. That TP-Link Wi-Fi antenna is very usable for it, but challenging. You need a good preamp. Okay? You can find tricks on the UHF Satcom. I don't know if you know that website. That's the godfather of the amateur DSN listeners. That's Mike Zero Echo Yankee Tango. That's Paul Marsh. It's the guru. It's the founding father. A person which I have a lot of things have learned from him to do. He is the moment that they launching a satellite from Florida. Every satellite of every rocket who is launched in Florida must pass England. So the moment it passed England, he already knows the frequency. He already knows what equipment they are using and how the orbit is going for that rocket. A dish of 1 meter is enough. S-band and, for example, the Lunar Reconnaissance Orbiter, that is a spacecraft who is orbiting the moon. It's very easy to hear, but you have to listen to DSN now and look when the NASA is communicating with LRO. That moment you can also aim your antenna to the moon and see LRO, the carrier of LRO. It has also a website where you can see the current location. That's something who isn't right here. The X-band, the only one on X-band here is stereo A and B. The rest is on S-band. That's all spacecrafts who are used to investigate the sun. Stereo A and B. Stereo A is one of the most powerful transmitters we can use to receive on the X-band. It is used for investigating the sun. the sunstorms. Stereo R, the R from ahead, and stereo B from behind. That stereo R is a little bit closer by the sun, and stereo B is a little bit further than the sun. Dus ahead of the Earth, and B is behind the Earth. We have a lot of satellites there, but what we must know, if you work with satellites around the Earth, it's always a circular orbit or an elliptical orbit. In our solar system, we have other things. Lagrange was a person who has calculated that there are 5 places in our solar system where the retraction and the repulsion crafts of a point is 0. So if you put a spacecraft in one of these points, you don't need energy to rotate with the Earth, so that it's very interesting. The first point is Lagrange 1. It's between Earth and the Sun. They are using Lagrange 1 for spacecrafts who are investigating the Sun. That it's one big problem with it. If you want to communicate with it, you have always the Sun on the background, who is a very big source of noise. So what they are doing, they are putting the spacecraft in a halo orbit around the Lagrange 1. So you can always put the antenna away from the Sun to communicate with it. Lagrange 2 is behind the Earth. That's the point where the telescopes, the space telescopes, are stationed. The James Webb telescope is stationed on Lagrange 2. Why? Because they are always in the shade in the shadow of the Earth. So they have a very good sight on the universe without problems with the Sun. There was one problem, they have solar cells. So to have energy, they put also a halo around Lagrange 2, so they can sometimes pick some energy from the Sun and they go back to the shadow side around Lagrange 2. 4 and 5 are 2 points where there are rest rocks, also meteorites, asteroids, who are rotating around the same orbit of the Earth. And we have Lagrange 3, who is laying behind the Sun, who is very good for conspiracy theories of a hidden world, and so on and so on. That's but that's not our interesting for the moment. So SOHO is on Lagrange 1 here. Lagrange 2 is always on the shadow. Here, Lagrange 3, the hidden planet. 4 and 5 is not so interesting for satellites because you have a lot of rocks there. So you have a lot of problems with damaging your spacecraft. SOHO is the one with the halo. ACE is a very special one. They put H on Lagrange 1 on Lissajous orbit. So that's the orbit of that ACE. I don't know what they have done to do it. Is it for accident or not? But that's the way the ACE is rotating around L1. Observations, that's a very old observation here. That's an observation of the LRO, the moon orbiter. You see practically no signal here. That's I have better things of photos, opnames, just a minute. Tianwen, for example. I have here a picture of Tianwen. That's also a Chinese spacecraft who is orbiting around the moon. You can here with the TP-Link antenna with a good preamp. You have Tianwen. That's a very easy one. The Mars orbiters are much difficult, but I think I have a picture of it here. With Yahoo. No. It's always the same. If you want Tian He, is that... yeah, I think I've got him. That's Tian He. That's a Chinese spacecraft who is orbiting Mars. Thus, I have a feeder for 8.4 gigahertz and directly a converter to 1.5 gigahertz, and that's the place where I put my my RTL dongle in it. So you see here, the carriers of it, it's not too big. But that's a signal who is coming from 300 million kilometers from space to my antenna. So you don't do it to decode something or to hear something or to decode pictures of the surface of Mars. If you want to do that, you are at the wrong address. That's the result you get and nothing more. It cost me 3 years to do it. That's but it's the way to it who is very interesting. The result, once you did it, you're no more interested in it. That's if you want to look how they do AMSAT DL. AMSAT DL, our radio amateur colleagues from Germany, from Bochum, have a YouTube channel where they have live, I will show you, where they have live and they have also in Bochum a dish of 25 meter. You have here the SDR play. You see here the receiving of Tianwen on 8.4 gigahertz orbiting the Mars. And you see a very bigger signal. And you see also the side lobes, something you cannot see with a dish of 1 meter. So they can see some things. No, it's a Chinese spacecraft, so you don't have very much information of it. But with the NASA spacecrafts, it's worth it to try to decode it. There are radio amateurs who are trying to decode it. But it's very difficult because you have no material. You don't find equipment second-hand or new very rarely for 8.4 gigahertz. The only thing I found is from our friends in Germany, Kühne Electronics, who has very professional material, but is also very expensive. I think the converter I have now at the moment is more than 500 euros. But if you look to all the things I have tried to build, I have spent more than 500 euros on garbage just to give it up and to buy something who is good. That's a lesson I take. But it's a really big challenge to receive it. Why? Because you must take in account this spacecraft is 300 million kilometers from here. It took 7-8 minutes from your signal to receive the Earth. So if you have a program who is giving you the coordinations from Mars, you are 7 minutes too late. The opening of my antenna is less than 1 degree. So in 7 minutes, you are already lost a few degrees. That's a very hard thing to find. What's also a problem, the speed of Mars is approaching Earth it is leaving Earth with a speed of 13-15 kilometers per second. It's leaving us very fast. So we have a very big Doppler. It could be 0.5 megahertz. It's 500 kilohertz Doppler. So you have to calculate it very accurately. Otherwise, you cannot find your frequency. You can say I have a Doppler, I have a dongle who has a bandwidth of 2 megahertz. The bigger your bandwidth, the weaker your signal. Thus you have to look very small. You have to average your signal, but that means that you must be perfectly on this frequency, which is a very big challenge. The first time I have received Tianwen, I have looked just the signal for 2 hours without speaking a word. And that was after 3 years of searching, and now I can't remember the time I did it again. That's but it gives a very good satisfaction. And our friends in Germany gives us an exact frequency, so they are very helpful for us. The normal thing I do is an antenna, a preamp, and I have a receiver, AOR R5000, that's a receiver, and I take the EF frequency of 10.7 megahertz on a dongle to SDS sharp. So that's the setup for me. Quick Yago, I have other observations. That was my antenna, my first antenna for the homemade field for S-band. The people who are doing QO100 and who are doing who are building self antennas are recognizing this thing. I never have won a beauty contest, but it works. That's Mars. We don't know that Chinese spacecraft what they are transmitting, but MRO has a traveling wave tube of 500 watts and a 3-meter dish. That Chinese spacecraft is stronger than MRO. Nu, MRO, that's the Mars Reconnaissance Orbiter. What you sometimes hear in the news that the rovers who are riding on Mars are transmitting images to the Earth. They don't do it directly. They're sending the images to a relay station, MRO, who is orbiting Mars, and MRO is transmitting it to the Earth. The rovers are capable to communicate directly with Earth, but they don't do it because it gives too much, they need too much power for this transmission. And this MRO, the meaning of NASA was to have 2 spacecrafts on Mars. One was MRO to have a relay station, and also a second one to be sure, but MRO is very good, works perfectly. So they didn't send a second one because it cost too much money. But if you see how much spacecrafts at the moment are orbiting around Mars, it's enormous. I think before Musk will put a man on Mars, they first will have to put traffic lights around Mars because they're gonna have collisions. I have tried to make something myself. That was a great disaster. You don't build feeders on gigahertz with only some copper and some solder. It doesn't work. You can buy something that comes from Netherlands, RF hand design. Very expensive. I have one who is the half the price, and septum feet I'm using. Preamps you can get secondhand on eBay. Amplitech is a good one. Problem is with Amplitech, they need forced cooling. They are cryogenic amplifiers, and it gets very hot. Kuhne has a preamp, but it costs more than 500 euros. But you are 200% sure it's a good one. Mixers, the mixers on eBay, about a low $100 you have a mixer. So you need your antenna, a preamp, the mixer, an oscillator, preferably with GPSDO driven, then a mid-frequent amplifier, and then your receiver. So it's not very easy. It's you have to build some things before it works. And the biggest problem is you don't have the equipment to measure. You always have to ask other people to measure something for you, and that's very very frustrating. But it gives a very good satisfaction the moment it works. Sonic, I'm at the end. Do I have gone over time?
You're absolutely fine, Bernard. That's extremely interesting and very, very good indeed. Lots and lots of food for thought there. And by the way, I put into the chat while you were talking a link to a talk that was given to us when we were part of Denby Dale Radio Club 4 years ago. It's available still on YouTube. It belongs to Pennine Ham. It's in part of our YouTube channel. And it was a talk by Professor Ian Morrison, whose call sign was G0DMU. He worked at Jodrell Bank, which is just outside Manchester, about 30 miles away from where I live. He's now a silent key. He died, I think, last year, Ian Morrison. But he gave a talk to us about the Jodrell telescope and what they were doing there, and lots of the things that you were talking tonight about pulsars and so on. He was talking about that. So anyone here interested, I put the link in there for the YouTube video from Professor Morrison's talk, which was extremely interesting. And it almost exactly 4 years ago to the day, Bernard. So the last time that in our radio club that we had a talk from someone to talk about radio astronomy was in June 2021. And now you've appeared and you followed on. You're the second person to give a talk on radio astronomy since Professor Morrison from the Jodrell Bank Telescope, now part of the University of Manchester. So you're in very, very esteemed company, Bernard.
I just searched something. I found something on the internet. You have a lot of information on the internet, but you have to be very careful because there are a lot of garbage on internet.
Indeed.
Who isn't true? That you can walk with your face to the wall sometimes. It's
yeah, indeed so. Ian Morrison was a very, very interesting speaker, and we did talk about arranging a visit to Jodrell Bank and meet him in person, but it was just towards while we were going through COVID, and unfortunately that opportunity never arose, which is a great shame, because I'm sure there are other radio amateurs that work at Jodrell Bank, but I don't know. I've never heard from them. Just the other thing, you were mentioning the unit, the Jansky unit. Of course, I think it was Jansky who discovered the Milky Way, wasn't it?
Yeah.
So very, very famous person in the history of radio astronomy. And that was not quite 100 years ago, but quite a long time ago, in the 1930s, I believe, between the two world wars, that he did that incredible pioneering work. So no, fascinating talk, Bernard. So I'm going to just see if we've got any questions or comments or observations that anyone would like to make to Bernard. Who'd like to go first? And that invitation is extended, of course, to our visitors from Belgium and Holland as well. If one of you would like to come in as well, you're more than welcome to do so. Wave at me, shout at me. Jeff, ON8NT, you were at the Leuven meeting. Just give us your sort of view of what you heard from Bernard and others at that conference.
Okay, thank you, Nick, and thank you, Bernard. Thank you very much for a very interesting talk. I think it's the second time I hear it now, and I understand now more than the first time. So it's a good thing that we put it on YouTube, and by looking and listening to it for a second or a third time, there is so much information that really have to trickle down into our brain, so to say. I think you are, and actually we all are examples, but you are a great example of a citizen scientist. I would call that a citizen scientist. I think most radio amateurs are citizen scientists, even by simply practicing CW. You just give data to the reverse beacon that is used to have some scientific research and so on. So I think you are really a good example of a citizen science, and I really appreciated that. I think all the talks in Leuven were excellent, but you were my favorite. and
Yes.
that's clearly that's personal. That's personal because I'm very much interested into space and to satellites and things like that. But of course, I'm not at all at your level, not even at your hips, I would say. So I have a lot to learn. But anyway, thank you very much for that, and I really appreciate that. I just had maybe one or two practical questions. Maybe could you mention the frequencies of the beacons in Zellebeke and in Durbe? Because that might be useful for people to look at. I will put it in the chat then. I think it's 143. No,
49.995, I think.
14. Yeah, just under the 50 megahertz
Yes.
band. And Durbe, is that the same frequency?
It's around it. I can't look. I can look for it, but
Okay, but it is just under the 6 meter band. So that means that
yes,
with your 6 meter antenna, or with any antenna, actually, you can
yeah.
actually
Yes,
look to that. And if you look up the periods of the meteor scatter periods, then you
yeah.
even have more chance to see pings and to
Yes.
to receive those things.
I want to mention you have a website in England, Triple M VHF, make more miles on VHF.
Okay, triple MVH.
And they have an alert system for meteors. And
Okay.
I was known that was a person from Gulf Italy or someone from the Northern Island who was live putting the graph radar on the internet. So you
Okay.
can see the pings passing. So you can also follow if it was worth it to do meteor scatter. And the time it was best worth it, it was when he has no streaming anymore. That means that he has shut down his system and he was taking his equipment to do meteor scatter. But I don't know if you do it further. It's a few years ago.
Yeah.
Already.
I remember you mentioned Paul March. Paul March from the UK, from UHF Satcom. I remember maybe 5 or 10 years ago, I attended the meeting in Ypres. He came to Ypres to give a talk, and that was also something very interesting. Really good
Fortunately, I
fun.
have missed that.
You have missed that. I was
Yes,
there. I was there.
yes.
Yeah, he's an excellent speaker, very humorous also.
Yeah.
And I really enjoy that. So maybe that's Paul March. That's maybe also someone that we can invite here at Pannenheim, Nick, one day or another. He is unbelievable.
25 years ago, he has started on a microwave meeting in England.
Yeah.
Freddie was there. Oscar November 6 Uniform Golf.
The famous Freddie.
And that was the time the first spacecraft went to Mars. When they were talking for, they were orbiting Earth just for launching to Mars. And they were, we must have something or we could receive it. And they have on this event, they have put some equipment together and they have received for the first time the signals of MRO.
Yeah.
That was a growing point of UHF.
I remember that he told that what was it, Rosetta? Was it Rosetta that he saw going down, and that the people from the NASA could not believe that he could receive that with his small dish. He say, "You are crazy," but he proved it because he had some proof to show them. Yes, I have received it. So
you have also a person in America, Scott.
Yeah, I don't know him.
He's on Twitter.
Scott Tilley.
Yes, Scott Tilley. Yes, Jan. Thank you.
Okay. And, thank you very much, Bernard. I don't want to monopolize the discussion, so maybe some other people can ask some questions or some comments.
That's a guy who is day and night. He is observing all the frequencies. He has found one day he has found a satellite who NASA has given up. And he has found the signal. He didn't know where it was. He was looking. He was monitoring it. He was calculating the orbit. That must be that satellite. And he has contacted NASA and he's got right. He has found the satellite
Yeah.
With NASA. But Paul Moss is also a co-author of the book Technical Handbook for Satellite Monitoring. I don't know if you know it.
No.
That's a book coming from England, I think from LSGB. No, or not. It seems very LSGB. The style of the letters, the style of the text is just the same, with a lot of information about satellites and the methods of demodulating and modulating and coding.
What's the title of the book?
Technical Handbook for Satellite Monitoring.
Okay.
Every year of every 2 years, there is a new edition with new satellites, new information, and so on and so on.
Okay.
Very interesting. Very interesting. Paul
Okay.
Moss is
Thank you.
co-author of it.
Yeah. Great. Thank you.
Yeah, thank you very much, Jeff, and thank you, Bernard, for the response to Jeffrey's comments there. Anyone else got any questions or comments they'd like to put to Bernard? Yes, Roger.
Thanks, Bernard. I was going to ask you whether there was still any possibility of the sort of the amateur discoverer still discovering things, but you've just given us an example there where a fellow discovered a dead satellite. There are still things that the amateur can find out even today without the really expensive 25-meter dishes and all that. I think
Yes.
it can be.
Well, I think Bernard's lost his internet connection there. Can receive space signals, but not us. I'm sure he'll be back in a minute. Yeah, Roger, I thought exactly the same. Your point you were just putting to Bernard there about is there still a place for amateurs and radio amateurs in this field of science? Can any of our guys do something that the professionals, making use of, the Jodrell telescope or the Merlin network we've got here in Britain and so on, whether there's still a role for radio amateurs?
My connection was gone.
Bernard, you're back. Yeah,
Yes,
we were
sorry,
saying,
my connection
I
was
just
gone.
I just made the observation. Yeah, we can hear the Deep Space Network, but we can't hear Bernard.
Yeah.
Maybe I can give an example of where we can still be useful.
Yeah, please. Yeah, go ahead, Jan.
The last couple of years, SpaceX has given the opportunity to, for example, small startups or universities to launch their CubeSat or 2-3 single CubeSat. Those are missions with 18, 19, and sometimes even hundreds of satellites in one time. Finding out who is really a very challenging task. So one of the things I do, and also some direct colleagues and other amateurs, is measuring Dopplers. So receiving signals on UHF, in my case also on S-band, and try to match or even calculate the TLEs, so the Kepler information for that specific satellite. And especially in the beginning of a launch, where the official institutes have no idea either, it's very useful, and especially small companies or universities reach out to us, and we help them. And this is just one example.
Yeah.
Brilliant. So you are the one who is giving the TLE data, Jan.
The preliminary TLE,
Okay.
especially in UHF. They come from a couple of guys, and most of them are also active on SatNOX, and provide those TLEs so that others can use them. Try to decode that telemetry, have an idea of the health of that specific satellite. We now had a launch of the very small satellites from Amsterdam, Spain, Haters ICM. The first TLE was created by the team I'm also a member of.
Okay, great. Yeah, I didn't know that actually.
It's good to hear that. You mentioned pulsars earlier, Bernard. Of course, I remember the story of how the pulsar was discovered. It's nearly 60 years ago, and it was just a university researcher whose job it was to erect these huge antennas. And then she noticed there was a little blip on the thing and said, "That's funny." And the story goes that her boss said, "No, no, it's just noise. Just ignore it." And she kept persisting and persisting. And you know, the person who's got an itch to scratch will get there in the end. And she didn't get the full credit. She's gotten it now, but at the time she didn't get the full credit. But she was noticed it. So there's always a place, isn't there, for the amateur. Not that she was an amateur, but you know what I mean. She was a researcher, like a student at the time, technically.
Mm-hmm.
Yeah, interesting. So thanks very much for the talk. Thank you.
That's if you try to receive spacecrafts from Mars, you see the result. It's not so great, but it's the way to the result. It's opening a whole world, a whole space you don't know. You must know something about launching the vehicles, how they are orbiting, how they are working, and that it's enormous interesting. That's the thing who is very attracted to it. The result is the result. That's almost nothing. That's
But the way to the result is the real thing, actually.
For example, there is a program from NASA, GMAT, Golf Mike Alpha Tango, and that's a program. You can develop your own spacecraft. You can say it has a weight of 100 kilograms. It has a fuel of that sort. It has a motor of that power. It has a load of that. And I want to launch it in Florida this time on that hour. And so you can see how much seconds it will last before it crashed. But it's a program who can simulate orbitings of spacecrafts. Scott Tiley is the person who is using it.
Okay.
He is measuring some radio signals, and with that radio signals, he is simulating orbitings to find out how they are. For example, if you go from Mars or from the Earth, first they are launching a satellite around the Earth, and then they are boosting it in a very elliptical way so that it can fly away to another planet. The theory and the mechanic to do it, that's amazing. How they are doing it.
But at the same time,
sorry, calculating the attraction of the different planets to go its way. That's GMAT. It's a very interesting program. You can also see in GMAT, for example, the ISS is a satellite who is not in a natural orbit around the Earth. It needs time by time. It needs a boost up because it has fallen several hundred meters to the Earth. You can see there is an example, a program to calculate how much power they need on how much time to give a boost to maintain his rotation. That's amazing. But I can work with it. It's too complex, and I don't have the time to ground it out. But it's very, very useful.
Bernard, maybe a personal question, and you don't have to answer if you don't want to. But what is your background? What is your professional background?
I've studied electromechanics.
Okay.
But that's a long story. But I'm working in the HVAC, heating, ventilation, air conditioning. I'm programming processes who are regulating temperature and climate regulations on hospitals, on all great buildings, not particularly.
Okay, great, yeah. So you don't have a background in science or in astronomy.
No.
You are coming from a totally different world.
I have passed my school time with much other things which I much regret.
Yeah, like everyone.
Like everyone, and
Yeah.
Bernard,
Okay.
we've got a friend in our radio club who gave us a talk a few months ago. Bob from Scotland has just written some articles in
Yeah.
our magazine Radcom, and he served in the Royal Air Force for many years in a senior position in the Royal Air Force, but didn't have a background in astronomy. But he was telling us when he gave a talk last time about a DX trip he made to the Pacific and was operating down there using simple vertical antennas by the sea and seeing what he could do with that on various islands. That having retired from work, he decided to do what he'd always wanted to do, and that is go to university to study astronomy. So he's been doing that the last few years, and he can't be with us tonight, in fact, because and I sorry, and I know Bob, you're going to be listening to this on YouTube or watching it on YouTube in the next few days. I'm just going to reveal something he said to me. He's writing a novel at the moment. Hopefully, Bernard, it's not a science fiction novel about Lagrange 3 and the whole theory of there being a hidden version of Earth, the other side of the sun. But it might be. I don't know. Science fiction is I've enjoyed some science fiction myself over the years, and it's very good. But what you've demonstrated tonight, Bernard, is our hobby, amateur radio. The thing that drew me into it, and I guess that probably applies to everyone else in this room, is just this amazing thought, and we can trace it back to, of course, that incredible scientist James Maxwell, a couple of hundred years ago. But this amazing discovery of the concept of electromagnetic waves, and still getting your head round that, and Maxwell, of course, was an incredible mathematician and physicist, and his books on it are the staple of work in universities. But
just the fact that you can say something in an equipment with an antenna, there is nothing around it, and 100 miles further, there is happening something. There's nothing between it, and it's while you're doing here something, you have a reaction. That's
and Bernard, even more than that, which it always fascinated me, is that if you operate QRP, for example, and you manage to make that QSO between, for say, England and Australia to VK running just 5 watts. Not even the power of a torch that you're holding in your hand at night time. But that has generated this electromagnetic field, this radio wave that has managed to traverse the entire planet and be received at the other end. Not only that, but if you're using, for example, CW, you're effectively coding that. You're sending a code which someone else at the other end is picking up and can understand what you're saying. I just find, as a radio amateur, that still, and I've been playing with the hobby since I was a young boy, that just entrances me as a concept. And that's what, I guess that's what leads people like you and Jan here in the meeting tonight, and others, to be so fascinated with space and radio astronomy in particular, and what can we hear and what can we receive, and what does it mean?
Well, I'm going to be honest, Nick. I've started the hobby on CB, Citizen Band, in the early 70s. I wanted to find a girlfriend. I found something else. I didn't find a girlfriend, but I found something else, and I don't know what was the worst.
Thank you for that revelation, Bernard. Henry, you've got your hand up there.
Yeah, Bernard, I noticed on the picture that you had about the Chickamauer reflector there, that you had some power lines in the background. Does local noise make any difference, or is it irrelevant on that sort of activity?
That was one of the things that this experiment didn't work. I have a local smoke, electro smoke like everyone from solar panels and so on and so on. That's the first thing. And the second thing I have, what I have learned also with DSN network, you need an amplifier with a high amplification. There's not only with a low noise figure, but you have to go above 50 decibel to have, you must take LNAs in cascade to make your receiver linear. That's the one. And the second is, and that was the bottleneck for me, that was, I think the distortion here around is too high, but I did it on 70 centimeters. You can, a pulsar, you can receive on every frequency you want. It's like the sun. The sun is also radiating electromagnetic signals on the whole spectra. But the higher the frequency, the lower the power density. So you have to make, it didn't work. And I don't know if I'm gonna do it again. I think about it,
You're
but
in
I
a
don't.
quiet environment. It's not really feasible unless you have a heavy investment in the equipment in between.
Yeah, they say that you need a bandwidth of 10 megahertz. But I challenge everyone to find on the amateur radio bands a bandwidth of 10 megahertz without spikes or noise. That's impossible.
S-band. S-band is possible. UHF is difficult.
S-band, but S-band is here is S-band is but you know the problem. I
yeah,
need
and I know what's coming on your side. So
yeah. I'm looking for that filter. On S-band, that's a problem, 2.4 gigahertz and so on. It's very close to the Wi-Fi band.
yeah.
And
one other thing, and I hope this is also interesting for others. What I also found out is that most LNAs can't handle the huge amount of ERP that's being transmitted by mobile transmitters all over the place. So they're completely overloaded and they're no longer useful on those frequencies. So what I did, and we're looking for the same bandpass filter, is use a bandpass filter for S-band between 2.2 and 2.3 with a very low attenuation. So I placed it in front of the LNA and it's working extremely well.
Yeah, well, why would it not? I mean, we use bandpass filters in amateur radio, and anyone who's used, even not necessarily. I mean, I discovered this not that long ago, actually, in the last few years. But I discovered that you might take a bandpass filter out into a field somewhere so you can operate two adjacent stations and not interfere. But actually, even with a modern SDR radio, putting a bandpass filter in line with it a good bandpass filter does make a huge difference in the received signals that you're receiving there, because all these other signals around are actually getting through and adding to the noise that's there. So what you've discovered on the S-band is undoubtedly the same as what we discover on HF as well and VHF.
Yeah. Most of the time we see that the LNA is placed in front of bandpass.
Yeah.
And I've turned it around.
Yeah.
But then you need a bandpass with a very low internal attenuation.
Yeah.
If you want a very good preamp, an LNA for S-band, there is one person who is making very good LNAs, and that's, I think, Mike 0 Delta Delta Golf or something. I will look for his call sign. If you ask it him, he will make one, and it's the best LNA I ever had. It's a hell of a Golf Delta Delta of Golf Golf Delta something. Jasmine, I will look it up.
DDK, I believe, G4DDK.
G4DDK, yes.
Yeah.
Yes.
Yeah.
That's
Well, the only problem with that one is that it's completely overloaded on S-band.
Yeah.
Due to the frequencies used by mobile telephones.
Mm-hmm.
Because I use that one. Okay. I believe another talk is being generated on the fly.
Without a doubt, Jan. Have we got anyone else before we kind of turn off the recording and thank Bernard for his contribution? Anyone else got a question or comment they'd like to make to Bernard? If not, can I just on behalf of Pen I Ham thank you very much indeed, Bernard, for giving us a very, very good talk tonight. Thank you very much.
Pleasure.
Let's show our appreciation as we always do.
Thank you very much.
Thank you, Bernard. Very, very enjoyable. I enjoyed it, and I'm sure others did as well. And this recording. So I'm going to say good night to those of us who've been, those people who've been watching us live on YouTube tonight. We get a few people who are at work and can't come to the meeting. They find YouTube is a nice channel to watch. And of course, we'll have people watching the film of this who are unable to be here tonight, and they may well make comments. So keep an eye on our YouTube channel, Bernard, in case there are people there with specific comments they want to make to you that you might want to reply to. But thank you very much indeed. So on that note, just a second, I'm just going to turn off the YouTube channel, and also so good night to those watching. And I'm also going to hit end record and thank our viewers who do catch up with the video later on. I hope you found this of interest, and I'm sure Bernard ON4CGX, if we've got any radio amateurs who have got specific questions they want to make to you, they'll find your email address on your qrz.com page, Bernard, and be able to drop you a note if that's okay with you.
Nick?
Yes.
You have my presentation on PDF. It's public. If someone is asking it, you can give it to everyone. That's no problem. That's
okay. Thank you very much.
There are no patents or how they call it. And my email address is on4cgx@gmail.com. That's if someone is trying something, I'm always prepared to help. It's I've done it all by myself. I know it's very comfortable if someone can help you.
And I'm just going to finish on this note. To your friends in Belgium who came along to laugh at your attempt to speak English and deliver this talk, I can truthfully say that your English is superb, and we all completely understood. Well, at least we understood the language, even if sometimes the technical data was beyond our knowledge, but was still of interest. So thank you very much indeed, Bernard. Absolutely superb.
I will hear it after the next local reunion.
It was excellent, Bernard. It was excellent. No problem at all.